you what Jones did, and that eventually led up to the Jones polynomial.
Okay. But what I want to announce is we don't have a break today. We decided we go 1 hour 20 minutes without a break. Okay?
All right,
Sounds good?
that sounds good.
Thank you, Erik.
Yeah, it's, last week I introduced you to von Neumann algebras and gave their basic definitions. I also introduced 3 different types. Type 1, where we can think about projections onto individual states. There's a minimal projection. We also talked about the fact that there could be finite projections, where you can order the projections. And then there was a distinction between type 1, type 2, and type 3. But in particular for type 1, there were 2 classes. One way to think about it is that even in ordinary quantum mechanics, we can make a distinction between finite dimensional Hilbert spaces and infinite dimensional ones. For an infinite dimensional Hilbert space, you don't have you do have a trace, but you don't cannot define the trace of the identity because, well, the dimension would be infinite. And for type 2 algebras, there's a similar distinction where there's type 2 infinity, where there is a trace, but the trace of identity is not defined. But type 2.1 is actually the class I will be talking about in this lecture, because it's in this class where von Jones actually, well, with his work, actually, he had a very nice construction of them that eventually led him to, well, the Jones polynomial, for which he also became famous. So this is a class of algebras where we have a ordering of traces, so every trace is finite, but also, and every projection is finite, but there's also a trace. So if I talk about
excuse me, Erik, about trace. Very long ago, when they tried, say in Gelfand's book, they tried to define dimension of complex group, complexified group,
yeah,
which is also infinite, right?
Yes.
So they tried to define trace of 1, which normally would be dimension of the group if it's compact.
Yes.
Diverges, and Gelfand very cleverly changed the subject, introduced densities, not the dimension.
This is actually going to be very similar because this trace which I'm talking about is not actually the sum of the states.
Yes.
So for type 2, 1, we cannot distinguish individual states because there's no minimal projection. So we cannot project onto states. So one way actually to think about type 2.1 is to think about a system of finite dimensional entangled say bits or qubits, where your algebra only can act on a finite number of them, and then you send the number of these bits to infinity. But your own algebra can only act on a finite number. So there is entanglement in the system, and your algebra only acts on half of sort of the system, so that you never can well, distinguish the individual states. Anyway, the trace indeed is not unique in the following sense that their identity. So if I have a trace, its defining relation is that it has to be cyclic. But any multiple of a trace is also a trace. And in this case, we will define the trace of the identity is indeed defined, but only up to rescaling. So we can define, normalize our trace now, and this is what most people do, so that this trace is equal to 1. So there's not going to be a number there that will tell me what the trace is. So I'm going to think about the trace as just something that I can normalize because the trace of the identity is finite, and then I fix my overall scaling so that that becomes 1.
In the other case, actually, because trace in representation depends on the representation, it cannot be 1. It is function which depends on the highest weight or something.
Yeah, okay.
Because it has to say which representation.
Well, actually, what I'm going to be talking about, and this is also what von Jones was interested in, is now how to relate different algebras, where you can think about sort of as different representations. And another thing that I sort of learned is that the way to think about von Neumann algebra is very similar to the space of functions that you can, on a manifold, that you can multiply. And of course it's non-commutative, so this is also why people like Kohn and so on eventually went to non-commutative geometry. So Kohn actually worked on the type 3 algebras, and that I will be talking about in the next lecture. Now I'm going to move to talk about type 2, which is where we have well, a bit more control. In particular, we have a well-defined trace, and we even have for type 2 a trace of the identity. Because now I can again go to what I call this DNS representation. So namely, I can look at the trace of two elements like this. So this must be a positive definite kind of inner product. So this is why I can write it like that. And the representation that acts then by left multiplication, you can think about as the regular representation. But there's also another representation of the same algebra where you act on the right, but you have to put a conjugate there in such a way that if I now multiply with another element, that they appear in the right order. So these two representations commute with each other. So if I think about this algebra, I'll write it like this. So I have two elements, A and B, and they form the algebra, which I denote by M. Then, of course, the product of the two is also in the algebra. The other thing we require is that there's a star operation, which I have in here. There's an identity in here. An algebra is also called a factor when the center of the algebra, namely it's the set of elements that are commuting with all elements in the algebra, is only the multiple of the identity. So there are no central elements in the algebra that we can define that are not multiples of the identity. So that's called a factor. And so what I said, this was called the DNS representation.
I forgot, is identity unique?
What do you mean by, is it unique?
Well, the general, I mean, it's just one element which will...
Well, of course it has the property that this is,
right.
I mean, this I guess is the only way that we define it.
The same question is if it's vacuum degenerate or not. So is it one element or there are...
No, there's only one element like this. And actually it's also one of the elements that we can put in here. So there is sort of like a ground state. It's really the state that we start from, which is the identity state. So there's a state which we call one.
And it's not degenerate, it's just one.
Yes.
What does it mean for two representations to commute with each other?
Well, you do two representations.
Actions can be not the representations.
Yeah, you said that these two representations commute.
No, sorry, I meant this.
No, you mean BA, I mean BA and B prime A.
Oh, sorry, what I meant to say is that there is I can represent this algebra on this Hilbert space in two ways.
Right.
Namely, one way where it acts from the left multiplication, and the other one where it acts on the right.
Yeah, so what does it mean?
So if I act with B, which is sort of from the left action, and so let me call it B left or B right, acting on the state, on any state, that this is equal to B right, B left, and we can check this, because one is multiplying putting B on the left, both are equal to this. This just doesn't, there's no ordering that you can multiply from the left and multiply from the right without them meeting each other.
So are you defining the trace in terms of an inner product?
No.
So would it be
Sorry.
inner?
The arrow is this way. This inner product is defined this way. So what DNS said, let's assume there is a trace. So DNS is Gelfand, Nijman, Nijmark, and Segel. They realize that when you have a trace, an algebra with a trace, then formally I can construct a Hilbert space out of where the elements of the Hilbert space are labeled by the elements of the algebra, where I define the inner product to be given by the trace. So this is the definition of the inner product. And so it's a formal construction where about because they eventually say that everything that I eventually want to compute with my Hilbert space will be in a product anyway. So anything that you want to compute in your normal sort of Dirac bracket notation, you can rewrite in terms of the trace, and then everything has a meaning. And that also defines the representation, and there's a theorem that for this algebra, basically this is the only representation that you have to carry. So what Jones actually was interested in, and that's are what are called subvectors. Because here you see basically that the algebra is mapped onto a Hilbert space, and I can also think about subalgebras. So what I'm going to assume is that there is some algebra which is also von Neumann algebra. So this was the one I started from, and I'm going to be interested in an algebra that is a subalgebra of that algebra. Personally, I like to think in terms of some pictures. So here I had two algebras M, and there's also a representation of a similar algebra which I call M prime, which is kind of what we have here. We have basically the action of all. I had a representation of the algebra on this Hilbert space, but there was also a representation basically of an identical algebra, which I gave the prime, which multiplied from the right, but they commute with each other. And I think about this in the following way, that there's the algebra M acting here, and M prime acting here, and just like in space-time where we want these operators to commute, these operators will also be commuting. So N then can be thought about as some part of this. So this is contained in the bigger algebra. It also has a complement, but then I think about that complement as sort of lying here. So there are elements of this M that are commute with N, which is kind of an important part. So there is an intersection of the complement of N contained in N. So N is a set of elements, just like this, but of course it's a smaller set. And they can still be represented on the same set of states. Now what Jones realized is that when you talk about these type 2 algebras, or it's actually more general, even von Neumann algebras, they're basically generated by projections. And one way I think about is that if you want to know to represent an operator, if you know it's some Hermitian operator, for instance, you know how to diagonalize it. But anyway, what he wanted to do is sort of define projectors associated with these subvectors. So the algebra M is a subalgebra of M. It also means that as a vector space, it's a subvector space of the big one. So what I'm going to first introduce is what's called a conditional expectation. Which is a map from the larger algebra to the smaller one. To make clear which element is part of this one and this one, let me denote them by little m and little n. Because I'm going to now talk about so if m is in N, then this object, of course, is in N, because it maps it onto here. I can also think about, of course, elements of N, and I can even take two of them. Because the property that this conditional expectation has to satisfy is that when I evaluate this product, so these are elements already of N. This M, of course, is not, but the rule is that basically the only thing that this E ceases to be N. So I can project, sort of apply E to M, and then I have an element of N, and I simply multiply that element either on the left or on the right with the element of N. So this is a property that we call a conditional expectation. It's a linear operation also, and so now I can define a projector on this algebra, so on this Hilbert space. So I'm going to define what I call the Jones projections.
So we don't know much about N. There are no special properties. Only property is that the N is also algebra.
It's also a polynomial algebra, so it has and it's a factor, so it means that it centers again on the multiple of the identity. It's closed, it has a star, it has all the properties of a polynomial
So
algebra, but
in regular language of things that we understand, it is, if M is a, let's say, real algebra, N is subalgebra.
that's correct. But now the idea is going to be that I told you about the existence of a trace for this algebra. There's also going to be a trace for that one, but it's not an identity element, because one way to think about it is that this actually acts on a smaller Hilbert space. So the identity element in this algebra may not sort of be having a trace which is equal to 1. I'm going to be able to project out part of the Hilbert space. So one way to think about this is that this algebra acts on a bigger Hilbert space that's obtained by tensoring the Hilbert space that this algebra acts on by an additional, small
Actually, in representation theory, if I have, let's suppose N is Cartan and M is Erik,
yes.
then if I take the generic state in the representation and I only know Cartan, I can construct the entire thing, as long as it's generic, as long as the eigenstate of Cartan, linear combination of Cartans.
But
Just
yes,
take the diagonal matrices and act on the generic state, which is a combination of the eigenstates, arbitrary one.
yes.
Unless coefficients are 0 or something except 1, this will generate all the.
I understand that. I think this is better thought of as in the way where you say this would be a product group and this would be a product group where you have fewer elements or something like that.
I kind of felt that having N one generic element in the Hilbert space, I could construct entire Hilbert space.
I'm going to do something similar.
Louis Gelfand, he invented it with Neimark in 1949, actually. What I just said is triviality.
Well, I think there's going to be a similar thing here. I'm actually, keep that question in mind for later. Because what actually will turn out, I'm going to actually introduce one more element, which is not an element of M, not an element of M prime, but sort of is associated to this inclusion. This is called an inclusion of a subvector, and it's going to be this Jones projection. So the Jones projection is an operator that can act on a state. Well, let me take. So so this n was an element of this algebra, so I construct this Hilbert space. So this is still, this spans basically the entire set of states associated with this Hilbert space here, but then I define it to be that one. So this you can think about, but basically as almost a projection on the level of the algebra, because here I project on the sub-algebra, but here I do it at the level of the Hilberts of the representation. Well, I keep the n, I mean, here I write sort of a curly n, here I like to write it more like this, write it easier. But it's associated to this subvector. Yes, so as I said, it's neither an element of m, neither an element of m prime. So what Jones then did is saying, well, let's think about this as indeed an operator also, and I can add it to my algebra. So the question is, well, if it's not a part of n, maybe you can show that. So we're going to start a sequence, namely I'm going to make a algebra which is even slightly bigger than n. So when I have this projection, I can add this projection to the algebra n. So I'm going to make an algebra which we call M1, which is generated by all the elements in M, where I add also the projection. And since I want to get a phenomenon algebra, what I do is, so this is the algebra I obtained by just adding this element, but I have to take its double committed. Because now I'm sure that I have a phenomenon algebra which is equal to its own double committed. So it's a projection, by the way, so I forgot to say, of course, everyone knows that projections will basically satisfy this relation.
So this algebra originally, every element had inverse or did not? I forgot. Or there was
No, they're an algebra. It's an algebra. It's not a group. And so the other thing that he introduced.
Because I'm trying to figure out why projection in general is not part of the algebra.
I'm a bit confused.
Linear combination.
You see here the capital E after little m is an element of n, and n is contained within n. But then, did you see that capital E after little m is not in n? I missing out something.
Yes. Okay. Let me try to make this clear. And actually, the calculation that I'm going to be mentioning will make that clear as well. But one way I think about it is that there is indeed an identity element in here. So I can, the thing about these representations is that I can get the entire Hilbert space either by acting with all the elements of M or with all the elements in M prime. So if I think about all of these elements which I call labeled by A, I can put a thought about them as I'm multiplying identity from the right with A star. And then I can still, in that Hilbert space, define the projection. And so there's some way that you see that that projection also does not commute with M prime. Because if I generate those things with M prime, I project, I start generating again, that action clearly doesn't commute. So En does not commute with all the elements in En, but also not with all the elements in M prime. So it is something that is not part of the, so if you ask what's being represented on this Hilbert space, it's not just this algebra, there's also this projection that's there. And I'm going to indicate in a picture already, maybe I can even do it in this picture. well, okay, maybe let me postpone that. Because there was actually one other thing I wanted to define, which had to do actually with these subvectors, which I forgot about.
I think what Brian was asking is that E of n is clearly element in M and N, because N is inside M.
Yes.
This one is, but I think you try to give the implication that this operation must be possible to implement it by elements of n, which is not true. So this operation, so En is not part of n, even though this is a part of n.
Okay.
So this is a part of n, but the operation that does this is not a part of n. So the thing that you have to keep in mind is that I'm defining now the action of this operator on these states. Well, this was an operation I did at the level of the algebra, and as you see, it has something almost like you put something on the left and the right in the same way, because otherwise I cannot do it. If you think about it sort of as a conditional expectation, it's not just an operation from the left, which is how the algebra n would act. The important thing about type 2-1 algebras is that when we talk about these inclusions, as I said, this you can think about as sort of acting on a smaller Hilbert space. And indeed, the trace of the identity is not the same here. Actually, it's the same up to a multiple. So the thing that Jones defined is called the Jones index. Or maybe I could even make it clear here, because if I would build a Hilbert space out of elements of n, it's clearly a smaller Hilbert space. Because this object is a projection, and a projection projects on a smaller subspace. So you can ask, by how much did we make the Hilbert space smaller? And that is defined by the Jones index.
So separately defined traces normalized in n and m actually will kind of contradict the projection, right? So suppose I separately define trace in n,
Yes.
which is trace 1 equals to
Yeah, so
n,
I should probably put an m here.
and then I define in m. And
So there's also a trace here, which is trace of n. And the trace of n is again defined this way.
Right, so the
But this trace is not obtained by just restricting this
Yes.
trace to elements in n. There's a factor.
so it's like dependence on the representation.
That's right.
So this E sub n plays the role of the identity element in M.
In a way, yes. Yeah, but you're right, because when I act on n, if I multiply by it, it leaves the state invariant. That's correct. I think it's one of the properties probably here that if I put an n here, of course, it gives me back the same state. But the Jones index, which is defined, denoted, first of all, by this. But then there are some formal definitions, which one way to think about is that, let me call this Hilbert space, which I constructed here, sort of H of n. There's a similar Hilbert space that I can construct with the trace in n. And then this index is the ratio of the sizes of the Hilbert spaces.
I think someone tries to get in. Can you? No.
The top of the room.
Right?
Yeah. top.
No.
No.
I think it's just draft or something. Another way of writing this is, which I anyway see mathematicians do quite often, is say that think about n as sort of the basic thing in which I can count things, so n is a set of generators, and I can think about n as sort of the module over those n's, and then you can take the dimension of n in terms of n.
Very similar really to Harishchandra and Gelfand for SL2C dimensions. That's how they introduce the density. They start looking at it.
I think it probably for a good reason, because in a way, as I said, a lot of this is developed on the intuition of measure theory on manifolds and so on. And even when we start talking about type 2-3, it's type 3 algebras, that's a very useful way of thinking about these algebras, is sort of as generalizations, as I said, of functions on manifolds, and those manifolds can have, well, infinite dimensional.
You know, the other ones, the Gelfand and Harishchandra, for complex groups, is very close to Verlinde algebra. Actually, it's one step from way it's written in the Gelfand mark how to define the notion of dimension. We know
Well, it's of course
What is,
related to character formulas, things like that.
what is the dimension of an infinite-dimensional Hilbert space?
that's what we will discuss.
Well,
Yeah,
I'm sure that we have to put the quotation mark. So the thing that is well defined in these algebras is precisely this ratio. So the index is well defined, even though each of those facts.
Can I try to answer this? Okay. So that was a question that they were asking. Suppose take SL2C. Let's say it has representation, it's infinite dimensional. How do we define the character or dimension? Dimension is trace of one. So they start thinking it, and they said, oh, this is very similar, like Dirac did delta function. Okay, so Dirac somehow departed the notion of the numbers, right, to define a dimension, and introduced the notion of densities and whatever, the distributions, right? So Harishchandra and Gelfand defined analog of delta function for dimension of the group, and then defined analog of character. So if you wish, introduce some distribution rho of lambda in the space, which is infinite dimensional, and define not the trace of one, but weighted with this rho of lambda, which is, there is a formula of dimension for, I ask you, what's dimension of the continuous series representation of SL2? What's dimension? No. There is a definition of something which perfectly works.
What happens if I change this way?
That's okay. So what I want to show is, first of all, intuitive answer is that I think about this representation as having a top, but then no bottom. It's the highest weight, but there's no, it goes all the way down, and no big deal. So I go down, and this is infinite. But then I have another one, which is starting here and goes down. And the question that I'm asking here is only about this difference.
Exactly.
I thought n contains the identity element. So your top is the identity element, is it?
No, let me think. No, actually. So, yeah, maybe I should give another, I'll give another picture in a moment, because I want to get to a graphical representation of these projectors, and I think that will make it clear as well.
You see, what you're trying to define is kind of regularization in some fancy way.
That's correct.
So, for example, let's go, I'm sorry, but can I little bit interfere?
It's
Just
okay.
one more.
All right.
So delta function, right? Let's take delta function.
Yes.
Sergei is absolutely right. What if I change the way I define it and multiply by 2? And I get 2 times, because at 0 it's infinity and everywhere else it's 0. No, we fix it by integral formulas. So we write that this delta function is such a distribution that
Well, but
integral is
this
smooth function.
is exactly this normalization.
Yes, yes.
Because the trace is the
Well,
integral.
that's not enough, right? Just one integral is not enough.
Integral is any smooth function.
Right.
Now, but here you take the trace over for the entire algebra, here you take it over a smaller part. And this is why there's a multiplicative factor between these two.
No, what I'm saying is that delta function, it's not sufficient to define delta function and just integral of delta function equal to 1. You have to say that integral of delta function is any smooth function
function is its value at what point, right? So the only thing you need here, I remember this, 1949, Gelfand-Meyer, Trudimian, it's a fat book like this. Everything of this is written there. Gelfand, 1949.
In a certain way, I think, of course, Jones knew all that stuff, but he extended it with a new idea, which is this index. And the program that he set out to do is to classify what all the possible numbers that this thing can have. So it's a positive number. You can think about it sort of as a dimension. And the way to think about it is that if this Hilbert space is equal to that Hilbert space times some other, so this is the way I think about it. Sort of again with some in quotation marks, I can think about this Hilbert space as tensoring some other Hilbert space here. And then we talk about the dimension of that Hilbert space. So these dimensions are infinite, but I can still talk about tensoring it with a finite factor.
So the factor space is this delta state, Hm over Hn.
That's correct. So this is also why it's sort of written like this. You think about M as a vector space, and you think about it as sort of being counted in how many times I can use this, put this one into that one.
And that's a necessary condition on N.
That's correct. Well, let's say this way, if this index is infinite, of course, then you cannot put it, but the fact that we had these finite projections, kind of, which was the assumption, even the defining property of these algebras tells us that these indices are finite. Although if you think about what are the possible values that you can get, now I have to admit that I have to write down, let me actually...
They're not all integers, are they?
These things need not be integers, actually.
Never.
Generally...
Never there integers, very only computation.
Right, so...
No, actually what turns out, okay.
Then
So
the speech is the factor space isn't quite correct, right?
it's a caricature. But the point is that this can be any real number larger than 4, and below 4 there's a discrete series of values, which, by the way, is connected to the Jones polynomial. It's precisely those discrete values that are actually, if you think about it, they're the quantum dimensions that follow from SU2 algebras.
Where does parameter comes? See, Jones polynomials is a one parameter.
Okay, I now have to look up the notes because I always forget the correct normalization. But there is a, so I'm going to say this will be a number, a positive number, but they can take any values between 4 up to infinity. I think 4 is included. But then there is a discrete set of values here, which are like the cosine squared of pi over some. I think I'm not doing this right.
That's how K comes in business.
So this is how the K comes in.
Because I remember that Jones polynomials are related to root of unity.
That's correct. So this is what he could show, that this union of so this is all everything larger than 4. Let me write my 4 book. And this is a discrete set, and I think there's a 2 squared here, so that this actually accumulates to 4. So it's a discrete number that accumulates to 4 and then it continues.
So basically, so the question is how to think about these polynomial algebras, in this case of type 2-1, as in a normal language of the representation theory, when we want to compare. In extension, what we do basically, we compare different representations.
That's
so
right.
he wants character, and character doesn't. So the guy wants some kind of notion of character.
So what I'm going to do now is I'm going to actually show you how to generate almost the entire algebra algebra, or even much more, out of only these projections. And then what he's doing is that he's going to show that these projections satisfy algebraic relations. The next step, he's going to search for representations of these algebraic relations, and then he classifies them. So that's the program.
Oh, good. The whole point is actually hidden in this n.
You start from this.
This n is the most important. Once you have n, you have a projection from m onto n.
And then you start adding, so then the next step, and this is the brilliancy of what he did, he realized that with using this projection, I can generate a next algebra, namely this one, and it's larger than the algebra n. And I'm going to show you in a picture how large the algebra is. Because what you basically do, maybe I should have said something about how to think intuitively about these type 1 algebras, which I have to admit I only read in these papers by Witten where they use this. Actually, this algebra appeared recently in the literature on the black holes in the Sitter space. Actually, this is the algebra that they claim is associated with the Sitter space.
Who claimed it?
Witten and Pennington, and I'll explain this in the last lecture. But there they also mention an intuitive way of thinking about these algebras, and I like to do this in pictures because it also will be the introduction to how to think about these projections. Well, actually, let me first since that is more intuitive angle, actually I'm going to continue Jones's thought a little further. First you have to accept that indeed this algebra is bigger than this one. And the way I think about it in pictures is that when I have this two algebras, n and n prime, that I define this way, where one acts on the left and the one on the right. There's also this involution that we can do that I call J. It's called Jn. It basically takes, there's an operation I can do which basically maps this one onto the conjugate of that one. So if I take it on B, which is an element here, I act with my conjugation, and then I get actually the B, which is an element here, but then it's star, and that's what this operation does. But in pictures, I think about this kind of as a way of indeed mapping this onto the other side, but by conjugating. So it's like a CPT conjugate, but the P part is really the reflection. And there's also a time reversal that you have.
I think it's a time, that's operator J called time reversal. V goes to B star under that.
Well, but it also reflects on the other side. So I would think about it as CPT almost, because it goes to the other side. So what we can do is take this algebra, take its complement, which is here, and then apply the J of this one. So there's actually an identity that tells you that this is equal to Jn n prime J.
N prime?
So n prime I mean the commutant. So the commutant I take n inside the representation. I ask what are all the elements that are commuting with n. That I call n prime. But n prime of course contains n prime, because if this is true, then you also have the relation that n prime is contained in n. Because n prime commutes with n, so it also commutes with n. But there are also elements in here.
Sorry, n prime is supposed to be n, Nancy prime, supposed to be isomorphic to Nancy.
So
N prime is a prime of n, right? Like you explained to us. There are kind of M and prime are.
Yes, but prime I mean all elements that commute with that set of algebra elements. That's what I mean by M. But there's also the J. The J is the thing that reflects here in this way.
I was confused. I thought that M prime would be sitting inside M prime, and not the other way around.
No, so N prime is defined as take all elements of all the things that can act on this Hilbert space that commutes with all the elements of N.
And that's bigger than N prime.
Yes, because N prime is contained in
All
N prime,
elements
because
of
everything.
Oh yeah, which comes with M prime commutes only with entire M. N prime commutes with the smaller one, so it's bigger.
Yes.
The more things commute
The
with
point,
smaller.
the
Yeah.
point is actually this is a very important idea. Is that
Oh yeah, I got that.
no, actually I want to write something here that there is an intersection of M with N prime, so that's non-zero. Those are now exactly the elements that I kind of had projected out. So N prime, so this was N, and this is N, which is contained in it. And so there is some set of algebra elements that are sitting here. That intersection is this intersection.
It's strange logically for me. Why don't we try to take N to be commutative somehow? N, elements of N to commute with each other.
That might be
Simplification.
I understand, but that's not going to get to the idea that Jones needed.
Because every construction depends on choice of N, doesn't it?
So yes. So we start with N, and then we suppose we're given an N, then we can start our whole story. And so what he basically wanted to do is find a classification of all of those situations. So for this situation, there is this number, which we call the index, and it's not like he wanted to construct a simpler situation, he wants to have a more general situation.
Classification.
But the thing that I want to show in the picture is sort of where this algebra N1 is sitting. Because when I do it like this, what you do is you take the commutant of this one, which is basically here, but then you have to reflect it into this point. So there's some algebra which is bigger, which is sitting here, which basically takes this one and then reflects it to this point, so we have it there. So M1 is sitting here and it's actually this algebra. And you see a little bit already in the picture that the size of this thing and that thing will be the same. So there is indeed a theorem that the index that I get here, that's also, so this index will also be the index of M1 with M. Because I now have started a sequence, namely this one is contained in this one, and then this one will be contained in this one. And of course now you see it happening. He just keeps going. So now I can repeat the story that I have here, and I can think about this as being contained in here, and start defining a En. Of course, what I have to do that is construct a GNS representation of this one. Again, define a projector, add that to the story, and so there's what's called a Jones Tower, where I make larger and larger algebras. So M1 is going to be the first one, and then it's going to be M2, and it's going to be M3, and so on. And I get a whole series of projectors that are constructed to all of those. So I don't think I need this here anymore. So I had an M, it was contained in N1, and there was also an N. What I'm going to do actually is think about a sequence, and in order to make it all consistent, I'm going to put a zero label on M, and what I called n, I called n minus 1. So I started here, which this was contained in here. I had a projector, and then I have a projector in here, and I keep going.
Okay, so it's kind of writing down SUN inside SUN plus 1, inside SUN plus 2, just simple for all of them projections.
Yeah, maybe. I think that could be like that. But of course it's much more abstract.
It's three-dimensional. Each of them is a three-dimensional.
It is, although these indices that I have there, which is now the theorem there, actually generalizes that the index of this one with respect to that one is going to be the same number. I'm just adding every time the same factor again. So every time when I project, I will be projecting a similar Hilbert space out of this. So what I'm going to be introducing then are projectors. This one I call E minus 1. There's an E0. Anyway, it keeps going. So I have eventually all the set of projectors where I start from and keep going up to infinite. So that's called the Jones Tower. You may wonder whether there is a generalization also that goes the other way. It is actually possible, but it's not unique. It's called the Jones Tunnel. But I won't need it. I mean, I will be talking about this tower because what I want to be telling you about is what are the operations or the relations that these things satisfy. We already know that each one of them is a projector, so they will satisfy these relations. But there will also be relations, in particular, it turns out that projectors that happen here and projectors that happen there, they will commute. But it will be neighboring ones that may be not commuting. And I'm going to actually represent these projectors graphically. And this is a good point to mention this sort of more intuitive way to think about these algebras. Because in a way what I've done here, I've shown that every time I think about adding one of those larger algebras, I'm actually factoring in a new Hilbert space. So every time I'm taking a new, this is sort of what I keep doing. If this would be sort of n, and you keep sort of adding n of them. Anyway, this is an intuitive way of thinking about it. But I think about these as only a part of the entire this, by the way, is a language that's more like type 1, where I talk about Hilbert spaces, but I don't really have type 1. I have type 2. And type 2 can be thought about as follows. I'm going to make a picture, a graphical representation of entangled pairs. So one way to think about this algebra is that I think each of those Hilbert spaces I associate to a line. So this is where one of those factors, so every time the factor looks like this, so also all of the intersections that I have where I take n plus 1 and intersect with the complement of n, that's the same. All of those algebras are identical. Because I can take indeed sort of the complement of this one where I ask what are the elements that commute with it. Part of the elements in here will commute with it, so there's an intersection between n3 and n2 prime. But that intersection will look isomorphic to this intersection. I mean, there's well, some map between those two. These algebras are the same in terms of relations and so on. So that I represent here now graphically, but important is that the state is actually entangled. So if I think about this Hilbert space where these operators are acting on, where I have m and n prime, that basically in the picture I do two sides of a space-time where m acts here and n prime acts there, but they're kind of acting on different bits or parts of the Hilbert space that are entangled with each other. And I like to represent it like this. So this is an entangled pair. And for instance, I can think about the Hilbert space, that this acts on, there's some other Hilbert space that the n prime acts on, and I sum over this. And one way to think about the index that I write there is how many states I'm summing over here. Namely, each of those algebras acts on a Hilbert space, but they are entangled with each other. And now I take, now maybe I should call sum over I up to, say, the index. But now I take many products of that, because that's what I was doing here. So I raise this to the power n, or k, let's say k. But then there's also still many other, well, let me write something like this. So, and then take a tensor product. And this n, I'll take to infinity. So there's an enormous amount of entanglement in the ground state, but the only states I'll be acting on are a finite subset of them. And that finite subset is what I have here. So now I'm going to actually draw a picture of these, for these projectors, that are going to tell me the relations I'm going to be having between these all these operations. Maybe I'll first try to tell you the relations and then write down the pictures.
I'm still not sure I understand what would mean the algebra of these projectors, because when we multiply closer, we project to smaller space, but we can't multiply in other order. Yeah, that's one projector. Suppose now I take EI times EI plus 1. That acts from big space to the second jump, right?
Yes.
I can't multiply other way around. I cannot write EI plus 1 times EI.
You
Because EI plus 1 acts from, I don't know, M2 to M1, and EI was acting from M3 to M2.
They're all embedded in each other, so
No, I'm saying that think this way. So one matrix is n times n minus 1. Another one is n minus 1 times n minus 2.
Okay, maybe let me
I
make
cannot
clear.
multiply n minus 1 times n minus 2 matrix on the right to the matrix.
Matrices are infinite-dimensional.
Yeah, but somewhere a trick is there. So I'm trying to understand how.
So let me write down a representation of them.
Okay.
So I'm thinking about building my GNS representation of one of the bigger ones.
Okay.
And now I'm going to represent the projection on this one and on that one.
Right.
So
That order I understand. But I cannot act first that one and then this one. It has to be M3 to M2, M2 to M1. But I cannot do M2 to M1.
no, but there's
times
a
M1
trivial
to
way
M3.
they
You just extend this.
extend the definition, because
Yeah.
if I think about, say, acting with, so if I take E1 for instance,
Right.
so I take it acting on M, and M would be, say, M which is sitting in 3.
Yeah.
Then this would be E1 and 3. So of course you might say this is sitting in, this element is sitting here,
Yes.
but of course it's a sub-algebra of the other one. So it's still part of the Hilbert space, and it's still an element of this one. So now I can act with E2 on it. And this object does make sense. But it kind of is doing trivial, because this is already in M1, and therefore M1 is contained in M2, and then this thing will just do nothing because we're already in M2.
So in this analogy of matrices, which we just extend with ones on diagonal. And
Something like that, yeah, so we can extend.
You can multiply matrices of different rank in any order.
That's right. But when the pictures are drawn, actually will become even more clear. But I'm going to first write down the relation. Indeed, the relation is that when I act with I plus 1, and I act again with EI, which I can do indeed in the other order. This is EI. And I can also do it with the minus sign, and that relation also holds. Except there is a factor here which I left out, and now I have to find the correct factor. Let me call this thing lambda. I think lambda.
What did you call lambda?
Lambda is this index.
Oh.
I will show you in pictures where this comes from.
Actually, can this be used as a definition of lambda?
Yeah, in a
Because
certain
it never
way.
really defines the dimension of this spaces, right?
I don't think I gave you the formal definition, let's say. So, yeah, so if you want to take this as your definition, then that's fine. There's still something I wanted to say, but now I forgot. Oh yeah, the name. This is the temporary lever. And I have to admit that I know about the name and the existence of this algebra for many, many years, but I never knew what it looked like or what its relevance was. But this is kind of where it comes in. And the key insight of Jones is that he realized that this algebra is related to the braid algebra. The braid algebras are very similar kind of relations, but it's not identical. But the beauty is also that he realized how to represent this geographically because that's also where we can understand these relations. So, and it goes sort of like the picture I wanted to draw here. Namely, I'm thinking about, and I'm sorry for putting the intuition here, still thinking about this tensor product because these algebras going to be acting on, so I'm going to actually draw lines for each of these factors. So I think about the algebra as acting on a Hilbert space where if I think about each of those factors as having a line associated, so when I put my hand here in the middle, I'm thinking about the algebra, which is the algebra that's in the component of this one intersected with that one. So I'm thinking about the entire algebra is basically constructed out of representations of these sequences, but each of these are acting on these lines. But now I'm going to represent my projectors by, well, maybe I should keep single lines because I'm drawing double lines so that they're more visible for you. But I think it makes it a little more complicated to talk about. So it's single lines. So each one of them kind of is a factor, but then the projector, so how do we think about this? So suppose these are the first two are here. This is going to be n minus 1 and 0x here. The n1x here and 3x here. So the projector that will project n0, yes, I'll do that. I will draw an E1. So I'm gonna, no, E0. So I'm gonna talk about the projector that identifies N0 in N1. N0 acts on these two, and 1 acts on these two. The state that we started from, remember when I constructed my representation, was the identity state. The identity state in the GNS representation of N3 is actually, can be thought of as entangling all of these lines with partners on the other side. The projector actually does the same thing, actually it entangles these two. So in order to project on this sub-algebra, I actually entangle these two. So as an operator, when I act on this Hilbert space, this is a projector, namely I project on an entangled pair. So this is E, say, so now let me define the other projectors and show you the relations.
10 minutes will be enough for you?
Actually, yeah, 10 minutes is fine. Actually, maybe I confused a sign here. Actually, I'll do something, but I think there should be lambda minus 1 here. Because I think my pictures don't work otherwise. There's some reason why there's a minus 1. So it's not the same. If I could define lambda like this, or maybe I should like this. So lambda minus 1. Of course, there's another way to define these relations. Let me do it like that. Because I'm going to actually redefine my projectors a bit. Well, let me first draw the pictures and then I'll do the correct way. Making them a little more round like this. So this is a projector, but there's also a projector that acts on the next one. So I can also have a projector that acts here. Let me take the first one again.
We are now constructing representations of temporary algebra.
I'm showing you the relation first.
Wait, on the pictures.
On pictures. So this was EI, say this is EI plus 1, and this is EI. And this is how I draw it in pictures, if I continue. But you basically see, you can straighten this out.
And you get the EI back.
You get EI back, without the normalization actually. What I've shown you now is this one. The relation that I also wanted to check is this one, which actually, if you draw it more naturally, actually has a factor in it. Because if I project like this, and project again, this is equal to indeed this, and then I have a closed loop. And this actually gives you dimension. So actually the dimension enters here. Of course I can rescale what I call the projector, and then the relation will enter there. So this is basically the generators, and if you take now many of them, the rule is that you can just keep multiplying these elements, and you can have many of them, but every time you see you're not intersecting any of those lines, they're not being intersected. So you don't immediately see, for instance, a relationship with the braiding group yet. But there's a fun fact about how many of these diagrams exist. So what I can do, if I look at this is called a temporary diagram. It has an even number of lines that are being connected with each other. So I mean, I have external points here that I've been connecting with these lines, and by using these projectors, I can make any diagram connecting all of them without them intersecting. I mean, you can draw many pictures like this, and then the number of diagrams that I can make will depend on how many external lines there are.
Constructs in not in one.
I will, well, that's, you know this, it's actually what's called scaling relation.
Yeah, Skinner or
Skinner.
Redemeister, whatever, Skinner relation. How do we get to that from here?
So what I wanted to tell you first actually is that if I think about many of them, so what you need to do is sort of draw many, well, there can be closed ones, but maybe let me actually just draw all the possible ones. One of the nice things you can do is you can make them turn around again and do things like this and keep going. And this would be an example of a diagram. And I have n lines at the bottom, I have n ones at the top. This, by the way, will be related to things on a sphere where I have 2n lines like that. And so we know, all right, so the relation that Jones realized should be holding is that what we are doing with knot invariance is also we're thinking about similar diagrams, but we are more interested in things like braiding relations. So braiding is more like that, where you cross them. But this is an operation I can also do on two of those lines, but then I will sort of exchange them like that. But there is a linear relation. He showed that it's possible to decompose this braiding operation as the linear combination of two of these kind of operations. In the sense there is some constant A where it looks like this, and a constant, I think it's A minus inverse or something that tells you. So this is doing nothing, and this is like doing this projection, and this is what the braid.
So this is 1 plus projector
For the braiding, that's correct. And the reason why this is possible is that if I think about this, so one thing that I can tell you is that if you ask how many possible diagrams I can draw that are connecting two n lines like this without intersecting, it's given by what's called the Catalan number. You take all, well, 2n is the number of lines. You take this binomial coefficient and divide by n plus 1. That's still an integer. And that number can also be thought about in terms of, what we know now that this is going to be related to the Jones polynomial. If you think about these Hilbert spaces, oh yeah, by the way, one thing that I should tell you, if you ask how many of these are there, it's 4 to the n. So this is actually an approximation. If you would use Stirling's formula, you get that this number goes like 4 to the n. Actually, it's smaller, slightly smaller. And there's a very good reason for it. If I think about these Hilbert spaces as just two-level systems, like spins, if I have 2n of them, I would get exactly a Hilbert space of that sort. So if I take the spin 1/2 representation of SU2, and I take 2n tensor multiple of it, and I ask how many times does the identity representation appear in it, it's exactly this number.
Yeah, this is very good actually, but one remains now is to explain why after he derived temporary algebra, why eventually ended up looking and finding dimensional representations of it. Because he constructed this in very huge infinite dimensional space.
Now, but he was interested in the representations of these. Why he looked at finite?
Yeah, E in this blackboard, that EI has nothing to do with any finite dimensional matrices or something like that. And here we will go now.
All right,
And
so
construct a projector in a 2n times 2n dimensional space.
Okay, I'll tell you, and actually this is exactly how I think that he didn't realize he was actually dealing with integers.
Right. So,
I counted these things, this is what the Verlinde formula does.
Right.
But what you actually can do is add many lines to them that you simply don't regard. So your algebra X here, and those lines are added and takes them to infinity. So it's basically looking at infinite dimensional conformal blocks, but only asks himself if I add more operators.
so truncation. How does a truncation come from the infinite dimensional one when you can truncate into the finite dimensional? So you are correct.
No, so he did not realize it could be truncated.
Oh.
So he basically classified it by looking at representations of the temporary or the break group. But that, okay, it's true that he eventually realized he had a representation of a finite dimensional one, but the problem that he set out had nothing to do with the finite dimensional.
Yes, that was the question.
So he basically realized that the representations he found could be represented on finite dimensional one. But so the Jones polynomial did not fit in the original problem that he was defining. So it was kind of like a byproduct of the things.
I get it.
And I understand now even these numbers, because they're actually the numbers that I would count. So I counted integers actually. So there's okay, maybe to finish the story. So if you take this number, as I said, you can construct it out of actually two representations and counting how many singlets you have when you take tensor products. But there is indeed in the theory of conformal field theory, there is a truncation of that where you go to actually to level k, where you have a smaller number. Then you have, instead of, you can actually write this in terms of characters, because you can actually multiply the characters and define the dimension and actually single out how many singlet states you have in there. That expression is actually the continuum limit of what's called the Verlinde formula. But the other thing is that if you take this product, this extra states in there, and you start taking the product of the limit to infinity, in the formula I wrote down, actually there's only one term that dominates, which is the one with the highest eigenvalue. And that's the one that defines the ratios of these representations. And actually, in that way, you exactly get these numbers. So by counting conformal blocks of SU2, you actually see these numbers appearing, and you understand the relationship with Kaufmann algebras. But it's because he thought the representations of this temporary leap algebra in the case when the dimension is actually smaller than the number of graphs that you have. So what he realized is that the number of pictures that he could draw, like of this sort, was actually larger than the Hilbert space that he was acting on. So it's like you're having a degenerate representation. Anyway, so
Can we?
I will probably just wrap up here, because actually this is kind of the storyline that he started out with quite an abstract problem. So I ended up with a Jones polynomial. The thing that I want to connect to later, when I come back in the lectures later this month, is these pictures. Because I mentioned already the words about that this might be thought about as entangled pairs. It's also how the connection with quantum information kind of will come in. I will probably elaborate on that further, but anyway, keep in mind a bit that these pictures have more general applications than just these Jones polynomials or not invariants. These pictures basically tell you how information flows. I think about them as that indeed you can have an algebra acting here, but you can also have an algebra acting there. And there's something called the Jones shift, which I'm also, or the canonical shift actually that I'm going to be mentioning later, is that there's some way that the operators that you can act here can indeed be sort of obtained also from here. This actually looks like what later will be interpreted like a quantum teleportation step, namely where you do projection on a bell pair. When you have here a bell pair, you can basically teleport the state from there to there. So this has applications into what's called quantum teleportation. And actually I've seen recent papers even explaining this. Actually I think even Kaufman, who's actually the one that came up with this relations like this, Kaufman, the one of the not polynomials, also realized that this algebra is actually one that is describing things like quantum teleportation. Because
this is your formula. Actually, in CFT, in formal field search, the reason truncation, there are double reasons for it, and the most beautiful one is that because you have not just while group, but you have affine while group.
yeah.
So while group identification, classification goes with shifts, and that shifts you cut the arc of
all that
where
is
the
not,
shifts are.
and no, all of that is totally hidden from this. Actually, one other thing I'm kind of confused about, I have to say, is that Witten, of course, showed that the Jones polynomial was related to knots in Chern-Simons theory, where you can have many gauge groups and so on. These relations hold when you start from the fundamental representation of an SU2 level K, or maybe for SUN you can do the same thing. But there are many other knot invariants that I can write down using this more general approach. So I'm wondering why those numbers don't show up in his classifications. But apparently, I think my explanation is that the fact that this is related to the break group is kind of a coincidence. It's sort of true only for those representations that he talked about, but there's not a general identification between the general leaf algebra and the break
There
group.
are other cases also. What you are saying basically is that this way, whatever it looks like it's a more general classification, and ended up with SU2.
That's correct.
Wow.
I agree, and I feel that when I look at my formulas, I probably can make algebras that don't fall in these classifications, but somehow there's something assumed in the steps that he did that don't allow those other representations.
Do we know other? I actually wanted now to irritate a little. We know other examples like
Probably because dimensions are always the same.
I was wondering that maybe even though it's another group,
no.
that the ratios of the dimensions might be the same because there's always an SU2 kind of embedded in or something like that.
Probably you need to invent some projection operators which will give you different dimensions. Like a flat manifold, you know, you can have kind of
Or they
This
all
is
hidden.
what I was saying. This is a flat SU.
Yeah, but here the difference in dimensions is always fixed the same, and in general flat
In
manifold.
flat manifolds, I can write any quiver. Okay.
Precisely.
And here, I'm sure it's possible to write any quiver. You see, in
Yeah.
that example that I was pushing on this embedding of intergroups,
Yeah.
right? It's just a quiver type.
Yes.
Okay, it's a not affine but regular. Then there is an affine. Okay, and then you can do arbitrarily what's called the ADE quiver, and there will be formulas which is connected to auxiliary matrices and all this kind of things. When he did that embedding, he probably picked not the most general way of maybe you can multiply 2, 3,
Yeah.
4. You can Dickin diagram just the max and so
Well, maybe, but I don't know where the assumption is because he clearly proved the mathematical theorem, and somehow there's the question is. But I also feel that maybe the other stuff is hidden in the continuum.
You know, I think some
or
people
something like that.
No.
Because what he does need is a very small representation, namely which is two-dimensional.
Right.
So how many of those
This guy,
other groups have
Barnata,
two-dimensional
remember?
representations?
There are guys in quantum groups who As you know very well, that this was understood by Torayev and Reshetich, that this can be translated into the Algebras and things like that. Right? And there we know that we have many classifications bigger, right? Probably those guys, maybe Parmesan or something, did understand that the John story can be made more general.
Yeah, I mean, there's many things that happened afterwards, which had these Bartelli diagrams and Opiano and people like that. They knew about this, and there's a story there whose literature I haven't sort of studied. And so it may very well that they realized, of course, when Witten wrote this paper, they must have thought about these other representations as well. And they also understood the connection with fusion rules and so on, because I think those Bartelli diagrams make use of that. And so this entered in the whole fusion category story. That, anyway, this is the way that John started.
Let's thank Erik again. I'm really looking forward to what you will tell us end of March, because this is kind of old stuff that we just remembered and so on. But you are saying that this all goes now to
Besides data,
let's go.
yeah.
I'm not announcing the question session because we are asking this very important.